Let's look at some problems to evaluating limits. Well, for this problem, you just evaluate directly the limit of x cubed as x approaches 2 is just 2 to the third, and that's just 8. Come over here, look at this one. You can definitely direct substitute or just plug in for x equal to 1, and so this just gives you 2 times 1 to the third. It's just 1 times 2 minus 6 times 1 plus 5. And so we get the negative 4 plus 5, and that just gives us 1. So what about this limit? Again, you can plug in, and so we plug in x equal to 2, we get the cube root of 12 times 2 is 24 plus 3 is 27, and so this cube root is just 3. Again, we can plug in. There's no discontinuity for the denominator. If this was x minus 1, you plug in x equal to 1, you get 1 minus 1. You have 0 in your denominator, so then we get nervous and scared. And, but we don't have to do that now. Just plug in x equal to 1. So we get 3 plus 5 is 8 all over 2. So the limit is 4. What about this limit? What happens when you plug in x equal to 3? We have the square root of 3 plus 6 is 9 all over 5. 3 plus 2 is 5. And so that just gives us 3/5. What about here, the limit of x as x approaches pi over 2? That's just sine of pi over 2. And so sine of pi over 2 is just 1. What about the sine? The limit of tangent x is the limit here as x approaches pi. We're going to break this up into parts. Tangent is sine x divided by cosine x. So the limit here of sine x as x approaches pi, well, sine of pi is 0, so this is the limit as x approaches pi of 0. Then the limit of cosine x as x approaches pi is 1, so 0 divided by 1, this is not undefined, this is defined. 0 divided by 1 is 1. So this is the limit of 1 as x approaches pi, and the limit of a constant is a constant. So the answer is just 1. That's 1. Maybe if I make the box first. Yeah. Come to number 29. So this is the limit as x approaches 1. This is cosine of just pi over 3. Okay. Now if you're like me, and hopefully you're not, sometimes I forget all these trig deviations and their values. So I take my good old equilateral triangle, label each side to be 2 because it's easy, and we divide one of them. Now if it's an equilateral triangle, that means that we have 60 degrees for each angle. And since we bisected this angle, so the one in there is going to be 30 degrees, right? So 60 degrees is our power of 3, and 30 degrees is our power of 6. Using Pythagoras theorem, this side is 1, and so this side right here would be the square root of 3. So then if that's the case, then the cosine of this power over 3 is the adjacent, which is 1, over the hypotenuse, which is 1/2. And you knew that already. And I do not memorize anything. Unfortunately, my brain is not so strong. I keep basic things and try to build on that, those basic notations in terms of what we may have need of. Okay. Well, let's look at some more. The limit of x minus 4 divided by x squared minus 16 as x approaches 4. And if you plug in x equal to 4, we get 0 divided by 16 divided by 16 is 0. This is the indeterminate form. Looks like we can factor our denominator. So this is the limit as x approaches 4 of x minus 4 all over x minus 4 times x plus 4. Now the x minus 4 will cancel out. We have left the limit as x approaches 4 of 1 all over x plus 4, and we just get 1 over 8. So indeed it was discontinuous at x equal to 4, but we removed that discontinuity. So we call this a removable discontinuity. Why is it doing that? Okay, good. The limit of the square root of x plus 5 minus 3 divided by x minus 4 as x approaches 4. Now let's look at that. As x approaches 4, we get the square root of 4 plus 5, which is the square root of 9. We get 3 divided by 3 minus 3, excuse me. So we get this 3 minus 3 is 0, and then 4 minus 4 is 0. We have a radical, so we rationalize. The previous one we factored, right? And then for the next one, we rationalize. So here, to rationalize, if the radical is in the numerator, obviously we're going to rationalize to get the radical in our denominator. And at the same time, we want to hopefully remove one of these discontinuities. So we have the limit as x approaches 4 of the square root of x plus 5 minus 3 all over x minus 4, multiplied to the numerator and denominator by the conjugate of the numerator. So this is the square root of x plus 5 plus 3 all over the square root of x plus 5 plus 3. So we multiply the numerator times the numerator. So this is the limit as x approaches 4. First time the first is x plus 5. And you know that since we multiply by the conjugates, the outer times the outer and the inner times the inner are just the opposite, so they cancel out. So this is just the last time the last, which is minus 9. This is all over. Leave that like it is. Just put parentheses there. X minus 4 parentheses the square root of x plus 5 plus 3. Now, yes, simplify the numerator. The limit as x approaches 4. Up top, we have x minus 4. And if all goes to plan, that's what's supposed to happen, because you want that guy to cancel out with this x minus 4 downstairs. So this is the limit as x approaches 4 of 1 all over the square root of x plus 5 plus 3. Now let's see if we can evaluate. Just plug in with direct substitution for x equal to 4. And this gives us, we just got a constant. The limit of a constant when x is 4 is a constant. So this is 1 all over the square root of 5 plus 4. The square root of 9 is 3 plus this 3. We get 6. Two special trigonometric functions. Again, we talked about this before in the introduction, but now let's apply it. So this number 63 is the limit of sine x over 5x as x approaches 0. But the theorem says that you got to have the form to match up. The limit of sine x over x as x approaches 0. We had another theorem that said that if you have a constant or a scalar times a function, you can factor out the constant times the limit. So we'll do that. So when you do that, this gives us 1 over 5 now times the limit as x approaches 0 of that sine x over x. Well, the limit of sine x over x as x approaches 0 is equal to 1 times the 1/5. So all we have here for your answer is just 1/5. Likewise, for number 64, the limit of 3 times parentheses 1 minus cosine x all over x. Well, it looks like this guy for the special limit for number 2, but we have a 3 there. So we're going to put the 3 out in front. Now times the limit as x approaches 0 of 1 minus cosine x over x. Well, the limit of 1 minus cosine x over x as x goes to 0 is equal to 0 times 3. So we got 3 times 0, and that just gives us 0. All right, let's look at this one. This somewhat combines two of those special function theorems. So let's see if we can break it down. I'm going to break this down because the limit of a product is the same as the product of the limits. So this is the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 minus cosine x over x. Well, the first term there is equal to 1, and the second one is equal to 0. So we have 1 times 0, and that just gives us 0. What about this one? Well, notice you can write this as the limit as x approaches 0 of sine x. Again, the limit of here, the product, is the same as the product of the limits. So this is times the limit as x approaches 0 of sine x all over x. Well, the first one, the limit of sine 0 is equal to 0. And then the second one, the limit of sine x over x as x approaches 0 is equal to 1. So we still get 0. What about this one? The limit of sine 3t over 2t as t approaches 0. Let's see. Well, the form says that you have to have this. You have to have the limit of sine x over x as x approaches 0 for this guy to come out to equal to 1. So x is generic, so it could be 3t, right? It could be house. Sine of house divided by house as house goes to 0 is equal to 1. So if this is sine 3t, then I have to have a 3t downstairs. So let's first write what I have by factoring out a 1/2. Okay. I can do that because this is not sine of some term. This is the 2t in the denominator that is completely disassociated with sine 3t. So this is 1/2 times the limit as t goes to 0 of sine 3t all over t. Can I take this t right here and put that in front of the limit? No, no, no. No, you can't do that because the limit is tending, right? It's changing with respect to t. So t is not static. T is moving, is changing. And because of that, we cannot touch it. We cannot manipulate it to put it in front of the limit. We're taking the limit of it. So this form here says that I got to have sine x over x. This is sine 3t over t. So what I'm going to do is to multiply by a sophisticated 1, and the sophisticated 1 would be 3 divided by 3. And so we're going to say a 3 here downstairs, right? Then we're going to put a 3 here upstairs. So 3 divided by 3 is 1, right? So if that be the case, I have not offset, have not harmed any lab animals in this process. So now the limit of sine 3t over 3t as t goes to 0, that this guy here is indeed 1 times 3 over 2. So this is 3 over 2 times 1. And so the answer is 3 over 2. And I want to say that's it. Yeah, that's it. Thank you.